Myself, B.Hemalatha, working as an assistant professor in Department of Electronics and Communication Engineering, Bharat Institute of Higher Education and Research. In this video, I am going to handle a course on control system. In that, we are going to discuss about the topic signal flow graph. Let's understand the concept behind the signal flow graph. First, we are going to see about what is meant by signal flow graph and the basic elements or terms which is related with signal flow graph I have listed here. First one is node, second one is branch, third one is path, fourth one is loop. In node, it is divided into three categories. First one is input node, second one is output node, third one is mixed node. And in path, there are four categories. First one is open path, second one is closed path, third one is forward path, and fourth one is forward path gain. In loop, it is divided into three categories. First one is individual loop, second one is non-touching loops, and third one is loop gain. All these terms are related with signal flow graph. Okay. After knowing the terms and the process of signal flow graph, using Mason's gain formula, we are going to obtain the transfer function of the given system. Then we will be seeing about a block diagram to signal flow graph conversion, and then how we are going to obtain the transfer function using signal flow graph analysis. Before entering into the signal flow graph, here in this video we are going to have a representation of a given system, that is a graphical representation of a given system will be used to find the transfer function of the system. So for representing the control system, there are two methods. First one is block diagram reduction technique and second one is signal flow graph. In block diagram reduction technique, we will be using blocks and summing point and the branch pointer. Using that three terms, we are going to find the transfer function. But accordingly, block diagram reduction technique for representing the control system or finding the transfer function of the given system is very accurate. But for complicated system, if you are going to use block diagram reduction technique, the system process will be more complex and then it will be very difficult to attain the transfer function for the given system. For that, a person called Mason's, he has found a Mason's gain formula so that we can able to analyze the same system graphically. Okay. For that reason, we are going to know about signal flow graph for representing the given system in terms of technical terms which has been given related with signal flow graph. Let us discuss about signal flow graph. It is a graphical representation of algebraic equation. Okay, so there in block diagram reduction technique, we are using blocks, summing points, and branch points. So by reducing the number of blocks, that is number of gain terms which is given in the block, we will be finding the final transfer function. Here, by using the nodes, we are going to find the transfer function of the given system. Before entering into the terms, first let us know about the basic elements of control system. First one is node. Here, it is a point representing a variable or signal. Take the example which I have given here. So here, nodes are nothing but Y1, Y2, Y3 and Y4. These are the four nodes which is given in the system. Here, Y1 is considered as an input node and Y4 is considered as an output node. Okay, and Y2 and Y3 is considered as a mixed node. I'll give the detailed description about each and every nodes which I've listed now. So node, it is a point representing a variable or signal. Next one is input node. It is a node which has only outgoing branches. Okay, so if you are taking Y1, it has only outgoing branches. Okay, if you are taking Y4, it has only incoming branches. So the nodes which has only outgoing branches are called as input node. The node which has only incoming branches are called as output node. Then what is meant by mixed node? If the node which has both incoming and outgoing branches, then that type of nodes are called as mixed node. So as I've said already, if you are seeing here, the nodes present in the signal flow graph, which is given here. This is a graphical representation of a given system. Okay, here the signal flow graph nodes has Y1, Y2, Y3 and Y4. These are the 4 nodes of the given signal flow graph. Here, as I said earlier, Y1 is acting as an input node and Y4 is acting as an output node. Here, Y2 and Y3 are called as mixer node. If you are seeing the arrow, it is having the incoming branches and the outgoing branches. That is, incoming branches gain is represented by B and the outgoing branches is represented by the gain minus D. Okay, so this A, B, C and minus D are nothing but the gains of the given system. So this arrow represents the direction of signal flow. Okay, so these are the basic things which we should understand about the nodes. Moving to the next one, branch. It is a directed line segment joining 2 nodes. It has both gain and direction. As I explained earlier in the previous slide, it has both gain and direction. Gains are nothing but A, B, C and minus D. These are the 4 variables represents the gain. And the signal from Y1 to Y2, there is an arrow. So the direction of signal is from Y1 to Y2. Here if you are saying from Y2 to Y3, from here Y3 to Y4. This is one direction and you can see here from Y3, it has a feedback path and again it is returning back to Y2. So this is having a feedback direction. These are called as feed forward direction and these are called as feedback direction. So these are all the instructions which can be obtained using the term branch. So the transmittance, the gain acquired by the signal when it travels from one node to another. Okay, the gain which has been acquired by the signal when it travels from one node to another is nothing but transmittance. This transmittance can be real or complex. Next term is path. It is a traversal of connecting branches in the direction of branch arrows. See here, if you are considering a path, it should not cross a node more than once. If we are taking the previous example, if you are taking Y2 node, it is starting from here and it is moving and it is reaching the node Y3. Again, it is returning back to Y2. So this is not considered as a path because starting and the ending point is of the node is Y2 here. So it will not be considered as a path. That's what they are saying. Path should not cross a node more than once. Next is open path. It starts at one node and ends at other node. It's called as open path. If I'm considering the same example, the node, if here the input signal is starting from Y1 and it is passing through Y2, again Y3 and then it is reaching Y4. This signal is called as open path. Okay, if you are considering the feedback signal here, it is starting from Y2, again it is reaching Y3 and returning back to Y2. So this is a closed path. That's what they mean to say. It starts at one node and ends at other node is nothing but the open path. It starts and ends at same node is nothing but the closed path. So what is meant by forward path? Path from an input node to an output node that does not cross any node more than once. Forward path means from input side to output side, the direction of signal is indicated, but it should not cross any node more than once. So if it is like that, that signals are called as forward path. What is meant by forward path gain? It is nothing but the product of branch transmittances of a forward path. So what are the gains which is present in the forward path will be getting multiplied, then you will be getting the forward path gain. So if you are considering from node Y1 to Y4 in this example, the gain products are A into B into C. These are the product gains of the forward path. That is nothing but called as forward path gain. Moving to the next term, loop. First one, let us discuss about the individual loop. See here, the same example I have taken here. If you are taking this diagram here, we are having Y2 starting in the signal is starting from node Y2 and it is passing through Y3 and again it is returning back to Y2. So the signal is starting from one node and after passing through a certain part of the graph, again it is returned back to the same node. But it should not cross any node more than once. Okay, so that type of that type of signals are called as individual loop. Okay, non-touching loop. For example, in the same thing, if you're going to have one more loop at the, if I'm taking here, we are having, this is one loop I said, right? Y2, Y3, and again it is returning back to Y2. So the signal is not crossing any other node more than once. Starting and ending point alone is same. Remaining all, only once it is crossing the other node. For example, if I'm having Y4 and Y5 here, okay, so the same feedback loop is also incorporated in this signal. For example, Y4, Y5, again it is returned back to Y4. So if I'm taking this loop and this loop, is there any connection between this? There is no connection between the first loop and the second loop. So at that time, these two loops are called as non-touching loop. I'll be describing this all these terms with an example. By that time, it will be very clear for everyone. So the loop does not have a common node. Why? Because in the example which I've considered, Y2, Y3 and Y2 is one node. Here Y4, Y5 and Y4 is the other node. So Y2, Y3 is no way connected with Y4, Y5. So that two loops are called as non-touching loops. Loop gain is nothing but it is a product of branch transmittances of a loop. So for the first loop, you will be having B into minus D. Similarly, for the second loop, what is the gain they have given? That will be multiplied. That product will be multiplied. So that is nothing but the loop gain. It is a product of branch transmittances of the loop. So here B into minus D. For example, if I am having here E into minus F means, so B into minus D into E into minus F. So you'll be getting BD EF. That will be the loop gain. Okay. So next, we'll all the terms which is related with signal flow graph we have discussed. Now let us move to the Mason's gain formula. This gain formula, Mason's gain formula, is found by a person named called Mason's. So only he is named like that, Mason's gain formula. What is the use of this Mason's gain formula is that this formula is used for finding the transfer function of any system graphically. Okay, so what they have given here, the gain between the input and the output nodes of a signal flow graph is nothing but transfer function of the system. It is calculated by using Mason's gain formula. Our aim is to find the transfer function for the given system. Either we can go for a block diagram reduction technique or for signal flow graph technique. Why we are preferring signal flow graph technique? Because for complicated system, it is very easy for us to find the transfer function in case of signal flow graph representation. But in case of block diagram, it will be a tedious process. But practically speaking, block diagram reduction technique will be more accurate comparatively to any other method to find the transfer function. So now let us discuss about the Mason's gain formula. What is T? T is nothing but a transfer function, which is equal to C of S divided by R of S are given. What is C of S? C of S is the output, R of S is the input. Why they have represented here as R of S and C of S? Because R of S is nothing but the reference input and C of S is nothing but the controlled output. So the output by input is nothing but the transfer function. We have already discussed in the previous sessions. That is, transfer function is not defined as the Laplace transform of output by Laplace transform of input, assuming all initial conditions are 0. So, based on that definition, we are writing here C of S divided by R of S, that is output by input. Here also we are going to represent in S domain, that is Laplace domain. So, only we are taking C of S and R of S. Okay, that is equivalent to summation I is equal to 1 to n pi del I divided by delta. Okay, so here pi, what has been given here, right? Pi is nothing but the representation of forward path. Pi is nothing but the representation of forward path. For example, if you are having 2 forward path, then I will be equal to 1 to 2. N is equal to 2 there. Okay, so if I am substituting n is equal to 2, then you will be getting P1 del 1 plus P2 del 2. Delta value is been depending upon the number of forward path, and this Pi also is depending upon the number of forward path. Let us discuss in detail when I am giving you the example how to solve the signal flow graph in order to find the transfer function. Okay, so here Pi is nothing but the ith forward path, and for calculating the delta value, there is a formula. delta is equal to 1 minus sum of all individual loop gains. What is individual loop? How many individual loops we are going to get for the given system, that will be added up. Okay, so sum of all the individual loop gains. For example, if you are having 3 individual loop gains, so you will be getting IL1 plus IL2 plus IL3. So we are adding all the 3 individual loops. Then moving on to the next step, that is plus sum of gain products of all possible combinations of 2 non-touching loops. So we can have 2 non-touching loops or 3 non-touching loops. That is, if as I explained earlier, if you are having 2 loops which is not having the common node, that are called as non-touching loops, right? So for example, if you are having 2 non-touching loops, NT-L1 and NT-L2. Okay, if you are having 2 loops like that, then we'll be adding the 2, NT-L1 plus NT-L2. That are called as 2 non-touching loops. If you are having 3 non-touching loops, then the next step will be carried out. Sum of gain products of all possible 3 non-touching loops plus etc. This is the way we are going to find the value of delta. And delta I is obtained from delta by removing the loops which are touching the ith forward path. So based on the forward path, we will be calculating the delta value, and here delta value is different. That is in the denominator. Del I is different. That is based on the formula which I have listed here. So this is about the Mason's gain formula. By using this formula only, we are going to find the transfer function. Let us move on to the discussion about conversion of block diagram into signal flow graph. So first we should know the steps to convert the block diagram into equivalent signal flow graph. First, what we will do is, as I said earlier, in block diagram, we will be having blocks. Inside the blocks, we will be having the gain values, G1, G2, G3, like that. They will be representing as gain values in the forward path. In the feedback path, they will be representing it as H1, H2, H3. According to the terminal it is connected. That is, if it is connected to positive terminal, then plus H1. If the H1 is connected to the negative terminal of the summing point, then minus H1 will be considered. So these are the gains which is represented in the block diagram. Second one is summing point. This summing point only is used for connecting the input signal and the feedback signal. And the takeoff point or branch point, we can say that branch point is nothing but like a node which is connected between the each and every blocks. Okay, so these are the 3 terms which is related with block diagram. So what we are going to do is, we are going to represent all the signals, variables, summing points and branch points of block diagram as nodes in signal flow graph. So first we have to check how many blocks. So according to that, we will be marking the nodes, and we will be checking about the summing points. There are 2 summing points means 2 nodes. Then 4 blocks means 4 nodes. 4 plus 2, 6. Then similarly, branch point is 1 means 1 branch point. So that is corresponds to 1 node. So first I said 4 blocks, 2 summing points, and then 1 branch point. 4 plus 2 is 6, 6 plus 1 is 7. So totally we will be having 7 nodes in the given signal flow graph. This is the first step which we have to carry out in converting the block diagram into signal flow graph. Moving to the second step, represent the blocks of block diagram as branches in signal flow graph. See, what is the use of branches? I said it is used for representing the gain and the direction of signal flow, right? So like that we are going to mark in the across the nodes. If gain block is connected between Y1 and Y2, then we'll be marking a direction of signal arrow from input to output side. There will be representing the gain as G1. Okay, it will be very clear when we are going to solve the problem. Okay, moving to the third step, represent this transfer function inside the blocks of block diagram as gains of the branches in this signal flow graph. This also I've said already. We are going to just mark the arrow. On top of the arrow, we are just going to write the gain of the corresponding system. For example, if there is no gain between 2 summing points or 2 branch points, okay, at that time what we will do is, we'll just mark an arrow in the forward direction and mark the gain as 1. If the gain block has not been connected between any 2 branches, then that is between summing points or between summing point and branch point, or between input and summing point, or between branch point and output. If there is no gain, we'll be marking an arrow and represent it as a signal of 1. That is, gain is equal to 1 we are going to consider. That is the last point which I have given here. That is, connect the nodes as per the block diagram. If there is connection between nodes, but there is no block in between, then represent the gain of the branch as 1. So these are the 4 steps which we are going to use for converting the block diagram into its equivalent signal flow graph. After converting, we will be using the Mason's gain formula in order to obtain the transfer function for the given system. Okay. Let us see one example. So they have given the signal flow graph. This is the signal flow graph, and then they are asking us to find the overall transfer function of the system. First, what is the first step? We have to find the forward path. We have to know what Pi. In the formula, do you remember? Summation I is equal to 1 to n Pi del I divided by delta. So first we have to find the forward path. Then only we can able to get the value of n, capital N. According to that, we can split the formula. So now Pi is nothing but the number of forward path representation. In this diagram, if I'm seeing here, the signal starts from input node to output node is nothing but the forward path, right? So if I'm taking here, this is Y1, Y2, Y3, Y4, Y5 and Y6. This is the nodes which is representing the forward path. That is, the signal is transferring from input node Y1 to output node Y6 without crossing any node more than once. So that is being considered as P1. P1 is equal to Y1, Y2, Y3, Y4, Y5 and Y6. So what are the gains there? That is nothing but the product of all the variables which is being given in the path. So here A into B into C into D into E is nothing but the first forward path. Second one is P2 is nothing but Y1, Y2, Y3. Then you can see here only the forward path we have to consider. So Y3 to Y5 it is directly connected. From Y5 it is moving to Y6. So what are the gains which is connected here? A, B, G and then E. That is what I have given. A product of all the gains in the second forward path. So see, you can ask me why we are not using calculating this one. Okay, this is nothing but the feedback signal. We are going to find out the forward path only in the feed forward direction. Okay, if I'm considering this one, the node starting from Y4, Y5, again it is touching the same node. So it cannot be considered as a forward path. Okay, so only 2 forward path. So it is clear that if you are having only 2 forward path, n value will be equal to 2. In the formula, if I'm substituting, that is in the Mason's gain formula, if I'm substituting n is equal to 2, then I will be getting P1 del 1 plus P2 del 2 divided by delta. So our aim is to find delta 1 and delta 2, and after obtaining that, we will be finding the del value, then we will substitute in the formula. Let us move to the second step. Second step is individual loop gain. So for the same example which I have shown in the previous slide, if I am taking this example, how many individual loops are there? There are 5 individual loops. Let me explain one by one. If I am taking this one, the first loop, it is starting from Y2, it is reaching Y3, again it is returning back to Y2. That is nothing but the loop. That is, loop is nothing but it starts from one node, after passing many nodes, again it is returning back to the same node. That is considered as a loop. So this is one loop here, Y2, Y3, again Y2. So what is the gains which is being present in that loop is B and J. So that should be a product value, right? So B into J is nothing but the representation of gains for the individual loop 1. So that's what I've given here. IL1 is equal to Y2, Y3, Y2. So for that, the gain product is B into J. Similarly, let us go for the second individual loop, IL2. IL2, they have considered Y3, Y5. Okay, then again it is coming here. If you are seeing here, Y3, it is moving here, Y5, again it is returning back to Y3. So what are the gains which is related with this loop? G into H. So this G into H is nothing but the gain product of second individual loop. That's what I've given here. Y3, Y5, y3, which is equal to G into H. This is the representation of second individual loop. Third individual loop, let us consider here, I'm starting from y3, okay, I'm passing through y4, again it is passing through y5, again it is returning back to y3, okay. So that is also one other loop, okay, y3, y4, y5, and again y3. So what are the gains which is related in this loop? Which is there, C into D into H. So CDH is the gain product of the individual loop 3. So that's what I've given. IL3 is equal to Y3, Y4, Y5 and Y3, which is equal to CDH. Next individual loop is IL4. If you are seeing here, I'm starting from Y4 and then I'm passing through Y5. Then again inside this loop, there is one small loop, Y4, Y5, again it is connected to Y4. What are the gains which is related with this? D into I. So D into I is nothing but the individual loop gain for the fourth one. IL4 is equal to Y4, Y5, Y4, which is equal to D into I. That is the representation of fourth individual loop. Next one is fifth individual loop. If you are taking here, it is starting from Y5 and it is again ending with Y5. So this is considered as other loop. That is nothing but F. So these are the 5 individual loops which can be obtained for the given signal flow graph representation. So this is the second step. Third step is we have to find gain product of 2 non-touching loops. Okay, non-touching loops are represented with NTL, that is non-touching loop. There are 2 loops. Let us discuss about how to write the expression for NTL1 and NTL2. So now, if I'm comparing the individual loops, first one with all the other loops, if there is no common node, that can be a non-touching loops. Okay, like that I can do, or otherwise from the diagram, by experience, we can able to directly write the expression from the given diagram also. For your easy understanding, let me say it from the individual loop itself. So if I'm considering individual loop 1, it is Y2, Y3, Y2. There are 2 nodes only, Y2 and Y3. Okay, if I'm comparing this first individual loop with second one, there is a common node called Y3. Okay, so it cannot be considered as a non-touching loop. If I'm comparing IL1 with IL3, there is also a common node Y3. So it is not non-touching loop. So, then I'm moving on to the fourth one. I'm comparing IL1 with IL4. We are seeing here Y2, Y3 is a node. Here Y4 and Y5 is a node. So these 2 individual loops are not having the common node. So this can be considered as a non-touching loop. That's what I've written here. Y2, Y3, Y2 is one loop. Y4, Y5 and Y4 is the other loop, which is having the gain product of Bj into Di. So the final product is Bj in Di is nothing but the representation of gains for the non-touching loop 1. Similarly, I am going to compare IL1 with IL5. So here Y2, Y3 is a node. Here only Y5 is the node. These 2 are not in having the common node. So that is considered as non-touching loop 2. So I have written this one Y2, Y3, Y2 and Y5 to Y5. These 2 loops are not touching. That is not, it is not having a common node. So I am considering that one. So here the gain product of first individual loop is Bj and the fifth individual loop is F. So Bj into F is nothing but the gain product of the non-touching loop 2. Okay. So from the diagram now it will be easy for you to understand. See, Y2, Y3, Y2 is no way having connection with Y4, Y5 and Y4 because this node is different, this node is different. That is first non-touching loop. Similarly, Y2, Y3, Y2 is no way having connection with the Y5. So that is considered as a second non-touching loop. Okay. If you're going to have one more loop here, for example, in Y6, as if we have it in Y5, if you're going to have one more gain loop here, then this Y2, Y3, Y2 is one loop which is not having contact with Y5. Similarly with Y6. So 3 non-touching loop. But for our example, what we have considered here, we are having only two non-touching loops. 3 non-touching loop is not existing in this example. Okay. So the higher number means we will be getting gain product of 3 non-touching loops. So we got all the gain products for each and every terms which is related with signal flow graph. Now we are going to calculate the value of del and del k. So here delta is equal to 1 minus sum of all individual loop gains plus sum of gain products of all possible 2 non-touching loops minus sum of products of all possible 3 non-touching loops plus etc. Okay, so delta is equal to 1 minus, we are having all the gains plus we are having all the gains of 2 non-touching loops minus 3 non-touching loops is not there, 0. See what I mean to say here is, in the previous slide, if you are taking Bj plus Gh plus Cdh plus Di plus F. That is the representation which I have given here. Okay, in the second one, the products of all possible combinations of 2 non-touching loops, right? So Bj Di plus Bj F is nothing but the second term in the delta value, and third term, gain products of all possible 3 non-touching loops is not here, is not available in this example, so I'm considering it as 0. Now I'm adding everything and we are finding the value of delta. We got the value of delta. So now we have to find delta 1 and delta 2. Why I'm taking delta 1 and delta 2 is, depending upon the number of forward path, we are going to calculate the del k. Okay, how many forward path we had for this problem? We had 2 forward path. Okay, P1 and P2. So obviously we'll be getting delta 1 and delta 2. Okay, so if how we are going to find the value? I've written here delta 1 is equal to 1 and delta 2 is equal to 1. How we are going to find this value? If you are considering the first forward path, see all the nodes are in contact with the first forward path. Y1, Y2, Y3, Y4, Y5 and Y6. So if all the points are connected, then delta 1 will be considered as 1. Okay, so similarly, if you are considering P2, if you are seeing here Y1, Y2, Y3, Y5 and Y6. If you are taking this loop is connected with Y4. So that is also having connection with all the nodes. So at that time, we will be taking the delta value 1 as del 1 is equal to 1 and delta 2 is equal to 1. So that's what I have described here. There is no loop which is not touching to the first forward path. Okay, which is non-touching to the first forward path. Since no loop is non-touching to the second forward path, del 2 is also equal to 1. Okay, we have to consider the loop. We have to check whether the loop is not connected with the forward path. If it is not having connection with the forward path, then you will be writing that product term as delta 1 or delta 2 according to the graphical representation given in the system. Okay, so now we got all the values. We are going to just substitute in the Mason's gain formula in order to obtain the transfer function. That is the 5th step. T is equal to C of S divided by R of S, which is equal to summation I is equal to 1 to N Pi del I divided by delta. Now, and N is equal to 2, if you are substituting in Mason's gain formula, the terms can be expanded in like P1 del 1 plus P2 del 2 divided by delta. P1 is nothing but the first forward path. P2 is nothing but the second forward path. Delta 1 is nothing but the value of delta which is not touching the any loop. Delta 2 which is not touching the second forward path. Delta is calculated using the formula in the step 4. Okay, now we got all the terms. We have just substituting, and then we are multiplying the delta 1 value also. This is P1 gain product. This is delta 1 is 1. This is P2 gain product. The delta 2 is equal to 1 divided by 1. This is the whole term is representing the delta which we have calculated in the step 4. Okay, so now if you are going to multiply with 1, the same gain products will be obtained here. Therefore, the transfer function is T is equal to C of S divided by R of S is equal to A, B, C, D, E plus A, B, G, E divided by 1 minus B, J plus G, H plus C, D, H plus D, I plus F plus B, J, D, I plus B, J, F. This is the final transfer function of the given system. So just by calculating 4 terms that is related with the signal flow graph, we can able to obtain the transfer function easily. First, we have to find the forward path, second one individual loop, and third one is non-touching loop, and fourth one is finding the value of delta k, that is delta value, and fifth step is to find the del k. K will be equal to number of the forward path which we have obtained for the given system. Okay, so by using this 5 steps, it is very easy for us to calculate the transfer function using signal flow graph. Now, let us consider one example for converting the block diagram into signal flow graph. So, they have given, this is the block diagram representation which has been given. I told you, no, actually block diagram will be having the number of blocks. Blocks is nothing but this one, G1, G2, they have given, no, G3, G4. These are the blocks which are called as blocks. G1 and G2, G3, G4, G5 and all is nothing but the gain products in the forward direction. And H1, H2, H3 and H4 are nothing but the representation of gains in the feedback direction. So, for example, if you are taking H1, it is connected between from the node Y4 and it is connected to Y2. So, if you are seeing here in the summing point, this is nothing but the summing point. Okay, Y1, Y2, Y5, Y7 are representation of summing points. If you are seeing here for the first Y1 summing point, both the terminals are positive. So, you will be considering H2 also positive and R of S also is positive. But if you are considering the second node Y2, then Y1 output is nothing but positive value and the feedback value is H1, no, that is connected to negative terminal. You will be considering it as minus H1. Okay. So, similarly here, it's a feed forward. It is a feed forward. In feed forward also they have given the gain G4. It is connected with G4 means it's a parallel block representation. We can reduce using the feed forward path method. Okay, there is a representation in block diagram. Here, the last one is H3. H3 is also connected to negative terminal, so it will be considered as minus H3. So, as soon as they give the block diagram, what we have to do, we have to just first check how many number of summing points, blocks and branch points are available. First, what we have to see, for any system, there will be input and the output. Here, input can be represented as R of S, that is nothing but the reference signal, and the output is represented as Y of S or C of S, controlled signal. Okay, so first draw a straight line connecting the input and the output. From that, what is the first node we are having? Summing point. So, we will keep one node here and mark it as Y1. Similarly, second summing point, Y2. Then, we'll be having the next node is Y3. Y3 will be having Y4, Y5, Y6, Y7, Y8, Y9. We'll be keeping all this, we'll be considering all this as nodes. So, totally there are 9 nodes in the forward direction. Okay. So, how this gain can be represented? From Y1, Y2 to Y3, there is a gain block. So, we'll be keeping an arrow and then we'll be representing the gain as G1 at the top of it. Okay. It will be clear if I'm showing this diagram. See, first I've taken R of S and then Y of S. From R of S to Y of S, I'm just drawing a straight line. As I said, I explained earlier, Y1, Y2, Y3, Y4, Y5, Y6, Y7, Y8, Y9. These are the nodes which we had in the block diagram. So between R of S and Y1, if you are seeing here, between R of S and Y1, is there any gain representation here? No. So if there is no gain representation, I informed you to consider the gain as 1. So that's what from R of S to Y1, they have marked the arrow as in the forward direction and they are representing it, the gain as 1. Similarly, from Y1 to Y2, we have to check. So from Y1 to Y2, again there is no blocks. So we are going to have an arrow and then mark it as 1 here. That's what I did it here. So similarly, when you are going to move from Y2 to Y3, from Y2 to Y3, there is a gain representation which is given as G1. So Y2 to Y3, there is an arrow representation. It is marked as G1. Similarly, Y3 to Y4, the gain is G2. So I'm marking a arrow in this direction, that is in the forward direction. The corresponding gain is G2. From Y4 to Y5, there is no gain. Y4 is nothing but the branch point here. From Y4 to Y5, there is no gain. So it will be considered as 1. Similarly, from Y5 to Y6, there is no gain. It also will be considered as 1. That's what, see, Y4 to Y5 is 1 and Y5 to Y6 as 1. So when you're considering Y6 to Y7, there is a gain block here. Y6 to Y7, there is a gain block which is represented with G3. So I've taken Y6 to Y7 forward direction. The gain is represented as G3. Okay, similarly Y7 to Y8, Y7 to Y8, okay, there is no gain block, so it will be considered as 1. From Y8 to Y9, there is a block, gain block as G5. See, Y8 to Y9, G5. Y7 to Y8, it is 1. So this is all about the forward path. Now we have to consider the feed forward path and the feedback path. So where it is connected, let us consider H1 first. Okay, feedback path H1. So it is connected from the node Y4 and it is connected to node Y2. It is connected to the negative terminal, so H1 will be considered as minus H1. So we'll be connecting this from here, from node Y4 to Y2 and marking that gain as H1. That's what I've done it here. Y4 to Y2 it is connected and it is marked as minus H1. Moving to the second one, here it is connected from node Y8 and it is connected to node Y1. The gain here is H2. So it is connected to the positive terminal. I'm considering from Y8 to Y1, I'm considering that positive terminal gain as H2. Okay, it is in the feedback path. Let us consider here, there is one feed forward path. It is connected between the nodes Y6 to Y7. So from Y6 to Y7, the gain value is Y4, that is in the forward direction. You can see here, the arrow direction is in the forward path. Okay, Y6 to Y7 it is going. The arrow direction is Y4 here. That's what the gain I have mentioned here. The final one is, if you are seeing from node Y9, it is feedback signal. It is connected to node Y5 to the negative terminal. So it will be considered as minus H3. So Y9 to Y5, it is connected with a feedback signal that is nothing but the representation of minus H3. So this is how we are going to convert the given block diagram into signal flow graph. Okay, so after that, using Mason's gain formula, we can able to find the transfer function of the given system. So in block diagram, it will be very tedious because we will be using all the rules in order to simplify the blocks which is present in the signal, and then we'll be finding the transfer function. But in this case, directly using the Mason's gain formula, we can obtain the final transfer function of the given system. This is about a signal flow graph, and we have discussed about all the terms, all the steps which has been carried out, and how we are going to find the transfer function using signal flow graph. And if it is a tedious process, that is if it is a complicated system, instead of going to block diagram reduction technique, we can convert the block diagram into signal flow graph and easily find the transfer function of the given system. Thank you.